October 27, 1924. Bayway, New Jersey. Inside Standard Oil's refinery, Building 935 had already earned a name among the workers. They called it the Looney Gas Building. No one needed to explain why. Men moved between steel tanks and narrow walkways, handling a new compound that made engines run smoother, quieter, more powerful. At first, the symptoms were subtle. A tremor in the hands. A flicker of confusion. A sentence that didn't quite finish. Then it escalated. One worker began laughing uncontrollably. Another screamed that insects were crawling across his skin. A third tried to claw at his own face. Within 5 days, 5 men were dead. 35 more were hospitalized, many in restraints, some hallucinating, some unable to recognize their own names. But this is where the record becomes difficult to reconcile. Standard Oil released a statement to the press. The deaths, they suggested, were unfortunate. The men had likely overworked themselves. There was no indication of a broader danger. And yet, internal correspondence from the period tells a quieter story. The compound being handled in that building had a known effect. It had already caused illness during earlier testing. It had already forced at least one chemist to step away from his work for months. So a question begins to form. If the symptoms were already understood, if the risks had already appeared, why was production continuing at all? The official explanation held for only a moment. Newspapers reported the incident. Local authorities asked questions. And for a brief period, production of the compound, tetraethyl lead, was paused. But the pause did not last. Because the story of Bayway did not begin in 1924. It began 2 years earlier, inside a different kind of laboratory, with a different kind of problem. In 1921, General Motors faced a limitation that threatened the future of the automobile itself. Engines were becoming more powerful. Compression ratios were increasing. And with that power came an instability engineers could not ignore. Knocking. A sharp, metallic rattle inside the engine. Premature combustion. Loss of efficiency. Damage over time. It was not a minor inconvenience. It was a ceiling. And so General Motors assigned a chemist to solve it. His name was Thomas Midgley Jr. At first, the work followed a familiar pattern. Compound after compound was tested. Iodine. Alcohol blends. Various additives. Each offering partial improvement, but no definitive solution. Then something unusual appeared in the results. A compound containing lead. Tetraethyl lead, TEL, eliminated engine knock almost completely. It worked immediately. It worked reliably. It worked better than anything else they had tested. 3 observations, recorded in quick succession. It reduced knocking. It improved performance. It could be produced at scale. But there was a 4th observation, and it did not fit as neatly. During early testing, Midgley himself began to feel the effects. Dizziness. Weakness. Symptoms consistent with lead exposure. At one point, his condition became severe enough that he was forced to leave work entirely. For nearly a year. Researchers examining company correspondence later noted that the compound had already earned a nickname inside the laboratory. Looney gas. The same phrase workers would later use in Bayway. So another question begins to take shape. If the compound produced visible neurological effects in controlled laboratory conditions, what would happen when it was manufactured at industrial scale? At first, the answer seemed manageable. The danger, executives believed, was localized. It existed inside factories, during production, not in the final product, not in the gasoline itself, not once diluted and burned. That distinction became central. Because in 1923, General Motors did not walk away from tetraethyl lead. They formalized it. In partnership with Standard Oil of New Jersey and DuPont, they created a new entity, the Ethyl Corporation. The name itself was carefully chosen. Lead was avoided entirely. Corporate filings from the period show a clear objective. Patent the additive. Control its production. License its use. A revenue model built into the chemistry. And yet, within the same research files, another detail appears. There was an alternative. Ethanol. Grain alcohol had been tested alongside tetraethyl lead. It reduced engine knock effectively. It burned cleanly. It did not produce the same toxic side effects. It also had one critical limitation. It could not be patented. No exclusive rights. No centralized control. No long-term licensing structure. Researchers like William Kovarik, examining these early decisions decades later, noted that the choice between ethanol and tetraethyl lead was not purely technical. It was economic. One compound offered safety and accessibility. The other offered ownership. And that is where the investigation shifts. Because by the time workers in Bayway began to hallucinate in 1924, the decision had already been made. The patents were filed. The partnerships were signed. The product had a name. And the question was no longer whether tetraethyl lead was dangerous. The question had become something else. Whether the danger was acceptable. The public explanation could not hold indefinitely. 5 dead workers had a way of attracting attention. Newspapers across the country began to report on the incidents at Bayway and other facilities. The phrase loony gas appeared in headlines. Questions reached Washington. And in 1925, the U.S. Public Health Service convened a conference. At first glance, it appeared to be a neutral investigation, a gathering of experts, a scientific review of the evidence. But when researchers later examined the attendee list, a pattern emerged. The industry had arrived prepared. Approximately 30 scientists present at the conference had direct or indirect ties to the ethyl corporation. Funding relationships, institutional affiliations, ongoing research support, independent voices were present. But there were only 3. That imbalance did not go unnoticed. Among those 3 was Dr. Alice Hamilton, one of the leading experts on industrial disease in the United States. She had spent years documenting the effects of toxic exposure in factories. Lead poisoning was not theoretical to her. It was observable, repeatable, already understood. Her warning was direct. You are doing an experiment on the entire population. A short sentence. A clear sentence. A sentence that appears in the conference record. But this is where the structure of the investigation begins to shift. Hamilton was not invited back for follow-up discussions. Her position did not shape the final recommendation. And when the conference concluded, its findings were carefully worded. There were, it stated, no grounds to prohibit the use of leaded gasoline, provided certain precautions were taken. Precautions. The word appears repeatedly in the final report. But when historians later reviewed regulatory records, something became difficult to trace. Those precautions were never formally defined. They were never enforced. They existed in language, but not in policy. And so the next phase of the system began to take shape. Because the question facing the industry was no longer whether tetraethyl lead posed a risk inside factories. That had already been demonstrated. The question was whether it posed a risk outside them. In the air, in cities, across entire populations. To answer that question, more studies were needed. And those studies began almost immediately. Universities were selected. Harvard, Yale, the University of Cincinnati. Respected institutions capable of producing credible results. Funding arrived through the Ethyl Corporation. The conclusions, published over the following years, followed a consistent pattern. No significant public health risk. Safe under normal conditions. No measurable danger at expected exposure levels. At first, the consistency seemed reassuring. Then another detail surfaced. Every major study reaching that conclusion had been funded by the same source, the Ethyl Corporation. So another question begins to form. What happens when the same institution that profits from a product also funds the research that determines its safety? The answer may lie in a less visible agreement. Because before the Public Health Service Conference, the U.S. Bureau of Mines had already conducted its own investigation into tetraethyl lead. Early findings raised concerns. But those findings did not reach the public. Contracts between the Bureau of Mines and the Ethyl Corporation contained a clause, one that would later be cited in historical research by David Rossner and Gerald Markowitz. The Bureau was prohibited from releasing its results without corporate approval. A small detail, buried in administrative language. But its implication is difficult to ignore. The institution tasked with evaluating industrial safety could not speak freely about what it found. And this is where the structure becomes clearer. First, the hazard is identified. Then, the investigation is organized. Then, the participants are selected. Then, the findings are filtered. Not hidden entirely. Not falsified outright. But shaped. Narrowed. Framed within acceptable boundaries. Researchers examining these patterns decades later would describe it not as a single act of deception, but as something more systematic. A framework. A way of managing knowledge. A way of deciding which questions are asked, which answers are amplified, and which voices gradually disappear from the conversation. And as the 1920s moved forward, the product remained on the market. Production resumed. Distribution expanded. Gas stations across the country began selling a new kind of fuel, marketed under a name that never mentioned its most important ingredient, ethyl, a word that sounded clean, modern, safe. But behind that word, the earlier question had not been resolved. It had only been deferred, because no long-term study had yet answered what would happen when millions of cars began releasing trace amounts of lead into the air. Not in a factory, not in a laboratory, but everywhere, all at once. For a time, the question remained abstract. Debates continued in conferences and journals. Industry representatives pointed to controlled studies. Independent researchers raised concerns about long-term exposure. The disagreement seemed technical, measured, contained within institutions. Then, in the 1940s, the investigation took an unexpected turn. Not inside a refinery, not inside a corporation, but inside a laboratory built for an entirely different purpose. Clair Patterson was not studying gasoline. He was trying to answer one of the oldest questions in science. How old is the Earth? Working at the California Institute of Technology, Patterson used a method based on uranium lead decay. By measuring the ratio of isotopes in ancient rocks, he aimed to calculate a precise age for the planet itself. It was meticulous work, sensitive work that required an environment almost completely free of contamination, because even trace amounts of lead could distort the results. So Patterson did something unusual. He built one of the first clean laboratories in the world. Air-filtered, surfaces controlled, instruments isolated from external interference. And even then, the measurements did not behave as expected. Samples taken from modern environments showed lead levels far higher than anticipated. At first, Patterson suspected contamination within the lab itself. Faulty equipment, impure reagents. But the pattern persisted. So he expanded the investigation. He began testing ancient ice cores, deep ocean sediments, geological samples that had been sealed away from human activity for thousands, sometimes millions, of years. What he found introduced a contradiction that could not be easily dismissed. Ancient environments contained extremely low levels of lead. Modern environments did not. The difference was not small. It was hundreds of times higher. In some cases, 600 to 700 times higher than what appeared in prehistoric samples. 3 observations, again, emerging in sequence. Ancient baseline levels were minimal. Modern levels were dramatically elevated. The increase began in the early 20th century. That timeline did not point to natural processes. It pointed to something else. Something recent. Something industrial. And that is where Patterson's work intersected, unexpectedly, with the history of leaded gasoline. Because when he mapped the rise in environmental lead against industrial production records, the curves aligned. The increase followed the introduction of tetraethyl lead in the 1920s. It accelerated with the expansion of automobile use. It spread across continents, carried not by rivers or soil alone, but by air, vehicle exhaust. In 1965, Patterson published his findings in a paper titled Contaminated and Natural Lead Environments of Man. The conclusion was direct. The lead present in modern human bodies was not natural. It was anthropogenic, human-caused. And the primary source, he argued, was gasoline combustion. At first, the implication seemed almost too large. If correct, it suggested that an entire industrial system, millions of vehicles, decades of emissions, had been dispersing a neurotoxin into the global environment. Not in isolated incidents. Continuously. Every day. So the question returned, but in a different form. If lead from gasoline was accumulating in the environment at this scale, why had it not been detected earlier? And this is where the response becomes more difficult to trace. Because Patterson's work did not simply enter a neutral scientific debate. It encountered resistance. Not immediate, not always visible, but consistent. Funding for his research began to disappear. Grants that had previously been available were no longer approved. The American Petroleum Institute, which had supported various scientific initiatives, withdrew backing from projects connected to his work. At one point, Patterson was removed from a National Research Council panel studying lead in the environment. A decision that appears in administrative records, but without detailed public explanation. There were also attempts, documented in correspondence, to challenge his position within the academic community itself, to question his methods, to isolate his conclusions, to reduce his influence. The Ethyl Corporation, whose product remained central to the issue, did not publicly concede his findings. Instead, the discussion shifted toward uncertainty, debate, the need for further study. And this is where the pattern begins to resemble something seen before. First, the evidence appears. Then, its interpretation is contested. Then, the conversation becomes prolonged. Years pass. Then decades. Patterson continued his work, refining measurements, collecting additional data, building a case not through a single paper, but through accumulation. Researchers who later examined his career noted the persistence required to maintain that position over time, often without institutional support. His conclusions did not change, but the broader system around them moved slowly. Regulatory action did not follow immediately. Lead remained in gasoline. Production continued. And so another question begins to settle into place. Not whether the data was correct, but how long a system can continue operating after evidence begins to contradict it. By the time regulatory agencies began to respond, the scale of exposure had already been set. Not gradually, not in isolated regions, but across an entire country. From 1923 to 1986, leaded gasoline remained in use in the United States for 63 years. It was not a temporary solution. It was not a short-lived experiment. It became standard, embedded into daily life. Each car, each commute, each ignition. And as automobile ownership expanded, so did the volume of emissions. By the 1970s, at the peak of production, approximately 200,000 metric tons of lead were being released into the atmosphere each year from American vehicles alone. Not stored, not contained, burned and dispersed. Into the air, into the soil, into the spaces between buildings, along highways, across neighborhoods. Government environmental reports from the period would later confirm the proportion. By 1979, nearly 90% of all lead emissions in the United States came from gasoline. 9 out of every 10 parts. A single source. But this is where the numbers begin to shift from industrial scale to something more difficult to measure. Human impact. Because lead does not behave like many other pollutants. It does not break down. It does not dissipate quickly. It accumulates. In bone, in blood, in developing brains. And decades later, researchers began to ask a question that had not been fully addressed during the years of peak exposure. What did this accumulation do? A study published in 2022 in the Proceedings of the National Academy of Sciences attempted to quantify the effect. The researchers examined blood lead levels across generations, comparing them with cognitive data collected over time. The analysis focused on individuals born between 1950 and 1981, the period of highest exposure. The conclusion was presented without dramatic language. Average loss, 2.6 IQ points. At first, the number seems small, almost negligible. But then the distribution becomes clearer. In heavily exposed urban populations, the loss reached as high as 7 points. Across millions of individuals. Across decades. A shift not visible in a single person, but measurable across a population. Researchers from Florida State University, working from similar datasets, estimated that approximately 170 million Americans alive today carry elevated blood lead levels linked to exposure during the era of leaded gasoline. 170 million. Not a subset, not a narrow demographic, but a majority of those born during that period. And this is where the scale becomes more difficult to visualize. Because the exposure did not occur in one place. It occurred everywhere. City streets, suburban roads, rural highways. Each vehicle releasing microscopic particles with every mile traveled. Each particle settling somewhere, layer by layer, year after year. And while the United States began phasing out leaded gasoline in the 1970s, with a full ban completed in 1986, the pattern extended beyond its borders. Other countries continued using it, some for decades longer. The global phase-out did not conclude until July 2021, when Algeria, the last country still using leaded gasoline, officially banned it. Nearly a century after its introduction. So another question begins to settle into the narrative. Not about discovery, not about warning, but about duration. If the risks were identified early, if the environmental accumulation became measurable by the mid-20th century, if the human impact was eventually quantifiable, why did it take 63 years to remove it from a single country's fuel supply, and nearly 100 years to remove it from the world? Lead does not disappear. That is the first detail researchers emphasize when they return to the data. Unlike gases that disperse or compounds that degrade, lead settles. It binds to soil. It lingers in dust. It remains in place long after the original source is gone. And over time, that persistence creates a second layer of the story. Because even after the last gallon of leaded gasoline was sold, the material it released did not leave with it. It stayed. Along highways, beside intersections, in the narrow strips of land where generations of vehicles passed within a few feet of the ground. Researchers examining urban soil samples decades after the ban began to notice a pattern. Concentrations of lead remained highest near older, high-traffic corridors, the same roads that had carried the densest flow of cars during the peak years of leaded gasoline use. A residue, mapped geographically, But this is where the investigation becomes more personal. Because soil does not remain outside. It becomes dust. It enters homes. It settles on floors, on windowsills, on surfaces that children touch without noticing. Studies conducted by environmental health agencies found that houses built before 1980, especially those near major roads, often contain measurable levels of lead and indoor dust. Not from paint alone, not from pipes, but from particles that entered through open windows, through shoes, through air, carried in over decades. And then another pattern appears. Children living near high-traffic urban areas continue, even today, to show elevated blood lead levels in routine testing. Not at the extreme levels seen in the mid-20th century, but above what modern safety standards define as acceptable. A quieter persistence. Less visible, but still measurable. So the timeline begins to fold back on itself. Because the exposure did not end in 1986. It changed form. From airborne particles to settled contamination. From immediate inhalation to slow, indirect contact. And this is where the narrative shifts from history to proximity. If you were born in the United States before 1990, it is likely that lead from automobile exhaust entered your body during childhood. Not through a single event, not through a known incident, but through accumulation, through air breathed near traffic, through dust carried indoors, through ordinary environments that appeared, at the time, completely safe. And this raises a more difficult question, not about the past, but about what remains. Because environmental surveys conducted in recent years still identify areas, particularly in older urban neighborhoods, where soil lead concentrations exceed the thresholds set by the Environmental Protection Agency. Parks, playgrounds, residential yards, places where the source is no longer visible, but the material persists. The experiment did not end when the product was removed. Its results remained embedded in the landscape. And when researchers traced the timeline back, the sequence becomes difficult to ignore. The risks were observable in the 1920s. Warnings were articulated in the 1920s. Environmental accumulation became measurable by the 1960s. But the product remained in widespread use until 1986. 21 years. After the data had already described its effects. 21 years of continued exposure. And so the question that emerges is not framed in technical language. It is simpler than that. What does it mean to run an experiment on an entire population without ever telling them it is happening? Thomas Midgley Jr. did not set out to reshape the atmosphere. He was, by most accounts, a practical chemist. Focused, methodical, the kind of researcher who solved problems presented to him. Engine knock was one problem. Refrigeration was another. And in the years after tetraethyl lead entered the market, he turned his attention to a different challenge. Safer cooling systems. At the time, refrigeration relied on substances that were dangerous in more immediate ways. Ammonia, sulfur dioxide, chemicals that could leak, ignite, or suffocate. Industry wanted something stable, non-flammable, non-toxic, at least in the conventional sense. Midgley and his team developed a new class of compounds, chlorofluorocarbons, CFCs. They appeared, at first, to solve everything. They were stable. They were non-reactive. They did not burn. They did not poison workers in the same visible way as earlier chemicals. 3 advantages, clear and immediate. And so they were adopted. Refrigerators, air conditioners, aerosol sprays, industrial systems. Over time, CFCs spread into nearly every corner of modern life. For decades, they were considered safe. Then, in the 1970s, atmospheric scientists began to notice something unusual. A thinning. High above the Earth's surface, in the stratosphere, a layer of ozone absorbs ultraviolet radiation from the sun. It is not visible. It is not something people experience directly. But it is essential. And measurements showed it was declining. At first, the data seemed uncertain. Then it became consistent. Then it became difficult to ignore. Research published in scientific journals suggested that CFCs, once released into the atmosphere, did not break down as expected. They rose. They accumulated. And in the presence of ultraviolet light, they released chlorine atoms that disrupted ozone molecules. One compound, one reaction, repeated millions of times. And gradually, the protective layer weakened. The pattern was familiar. A chemical introduced as a solution. Early assumptions of safety. Delayed recognition of long-term effects. And then, resistance. Debate over the data. Calls for further study. Time passing between discovery and action. In both cases, the effects were not immediate in the way industrial accidents are immediate. They unfolded slowly. Across years. Across decades. measured not in single events, but in trends. Midgley would not live to see the full consequences of either invention. He died in 1944, years before the environmental impact of CFCs was understood and before the long-term effects of leaded gasoline were widely acknowledged. But his work remained, embedded in two systems. One that altered the chemistry of the air at ground level, another that altered it high above. And this is where the narrative pauses. Because the documents that trace these developments, corporate records, scientific papers, government reports, do not suggest ignorance. They show awareness, gradual at first, then clearer, then increasingly difficult to dismiss. So the question that remains is not whether the risks were ever known. The historical record indicates that, at various points, they were. The question is quieter, more difficult to locate. How many similar patterns exist now? Not in the past, not in archived documents, but in the present, in products that appear stable, in systems that appear safe, in research that has already been conducted, already written down, already filed away, waiting, not to be discovered, but to be acknowledged. There is a tendency, when looking back at events like this, to isolate them, to treat them as products of a different time, a different regulatory environment, a different scientific understanding, a different relationship between industry and public health. And to some extent, that framing is valid. The early 20th century did not have the same tools for environmental monitoring. Long-term epidemiological studies were rare. The mechanisms of low-dose, chronic exposure were not fully understood. But the documents suggest something more complicated than simple absence of knowledge. Because the warnings did not appear suddenly in the 1970s. They appeared early. They appeared repeatedly. They appeared in different forms. Internal memos, laboratory observations, independent research papers, government discussions, not always aligned, not always amplified, but present. And when investigators compare this case to others across the 20th century, a pattern begins to emerge, not identical in every detail, but structurally similar. A product is introduced. A benefit is identified. A risk is observed. The risk is questioned. The research is funded. The conclusions are managed. Time passes. Then, eventually, the cost becomes measurable, not in theory, but in outcomes. Public health data, environmental accumulation, statistical shifts that only become visible when viewed across millions of people. Researchers studying regulatory history have noted this sequence in multiple industries, not as a coordinated plan, but as a recurring process, a way of navigating uncertainty when economic incentives and scientific evidence begin to diverge. And this raises a question that is less about accusation and more about structure. What systems exist to detect slow harm? Not immediate danger, not acute toxicity, but gradual effects. Effects that require years of data. Effects that are difficult to attribute to a single source. Effects that can be distributed so widely that they appear normal. Because leaded gasoline did not produce a single defining catastrophe. It produced accumulation, small exposures, repeated over time. And that kind of pattern is harder to interrupt, harder to regulate, harder to see clearly while it is happening. Government reports, reviewed decades later, often describe the phase-out of leaded gasoline as a success of environmental policy. And in many ways, it was. Blood lead levels declined. Air quality improved. Measurable health benefits followed. But those same reports also document the delay, the years between evidence and action, the period in which the data existed, but the system did not respond immediately. And that interval becomes the focus. Because it is not unique to this case. It appears in different forms, in different industries, across different decades. Sometimes shorter, sometimes longer, but present. So the investigation shifts again, away from a single product, toward a broader question, not whether mistakes were made, but how decisions are made when information is incomplete, incentives are misaligned, and consequences unfold slowly, and whether those conditions still exist. Because if they do, then the story does not end with leaded gasoline. It becomes a reference point, a documented example of how knowledge, uncertainty, and time can interact in ways that are difficult to recognize while they are happening. And that leaves one final consideration, not about the past, but about the present moment. What do we fail to notice now that will only become visible later? Thomas Midgley Jr. died in 1944. By then, tetraethyl lead had been in use for over 2 decades. Its production was expanding, not declining. The warnings had surfaced, but they had not yet altered the trajectory. Chlorofluorocarbons had already been introduced. Their adoption was accelerating. refrigeration systems, industrial processes, consumer products, all incorporating a compound that, at the time, appeared almost ideal. Two inventions, two solutions, both entering global systems before their long-term effects were fully understood. And for a while, both were considered successes. The documents do not suggest a single moment where everything was known at once. There was no definitive turning point where the full consequences became undeniable and immediate action followed. Instead, the record shows something slower. Fragments of evidence, distributed awareness, a series of signals that, taken individually, could be questioned, but taken together, formed a pattern. Corporate records acknowledge toxicity during early production. Scientific papers identify environmental accumulation decades later. Government reports eventually confirm widespread exposure, each piece appearing at a different time, in a different context, addressed by a different institution. And between those pieces, time. Years where the product remained in use. Years where the data existed, but did not yet reshape policy. Years where the system continued forward. The Ethyl Corporation, created to manufacture and distribute tetraethyl lead, continued operating under that name until 2004. Long after the product that defined it had been phased out. Long after the health consequences had been measured. Long after the regulatory response had been implemented. The name remained, a trace of the original decision. And when researchers revisit this history, they often return to a similar point. Not to assign a single cause, not to isolate a single actor, but to understand how the process unfolded, how knowledge moved, or failed to move, through institutions, how uncertainty was managed, how delay became part of the outcome. Because the question that lingers is not confined to one company, or one chemical, or one period in history. It extends beyond that. The records confirm that Standard Oil and its partners understood, at least in part, the risks associated with tetraethyl lead early in its development. That is documented. But that is not the most difficult part of the story. The more difficult part is what follows. What happens after the knowledge exists? After the data has been written down? After the first warnings have been voiced? Because history shows that recognition does not always lead to immediate change. Sometimes it leads to debate. Sometimes to delay. Sometimes to a continuation of the system, even as evidence begins to accumulate against it. And so the final question is not framed around certainty. It does not ask for a definitive answer. It asks something quieter. How many products in use today have already been studied, already been tested, already been questioned by a scientist whose findings exist somewhere in a report, or a paper, or a file, but have not yet reached the point where action follows? And if those documents exist, where are they now? And who has already read them?